Hi, let's talk about the motion of a pendulum. A simple pendulum. What makes it simple? For one thing, the string is so light that we can say it's massless. And we are assuming the string has a constant length L. In other words, it doesn't stretch. One end is fixed in place at O. A point mass, a particle with zero size and mass m, is attached to the other end. The mass swings back and forth. Period t is the time it takes to make one complete cycle. Angle theta locates the pendulum as a function of time. Let's make an FBD of the mass at the end of the string. There's weight down, mg. There's the tension force in the string. I know we usually call it T, but we're going to use T for period, so let's call it P for pull. And that's it. The body is not in equilibrium. Its motion, direction, and velocity change constantly. But point O stays put. Let's apply the rotational version of Newton's second law about point O. The net torque about O equals the inertia of the body about O times the angular acceleration. The tension force P passes through point O. What torque does it make? Yep, 0. We don't have to worry about P. The weight force makes a torque. In fact, on either side of the swing, it pulls the mass back to the center. Direction matters. This torque is opposite to the deflection angle theta. Opposite means negative. One way to calculate torque is force times perpendicular distance. The force is mg. The perpendicular distance is L, the length of the string, sine theta. So the torque is negative mgl sine theta. The inertia of the point mass about O is the mass times the distance to O squared. So ml squared. We can put these back into the Newton 2 equation. Negative mgl sine theta equals ml squared alpha. I know, we need to simplify. M's cancel. Wait, the M's cancel. The M on the left side is gravitational mass. The M on the right is inertial mass. Remember the principle of equivalence? They are the same mass, and so they cancel. Would you expect mass to affect pendulum motion? What did you observe in the lab? Did the period of the pendulum depend on mass? Hopefully, there's a resounding no out there in virtual space. The fact that mass does not affect the period of a pendulum provides us evidence for the principle of equivalence. we can cancel one L on each side. Let's get angular acceleration by itself. Alpha equals negative g over L sine theta. The angular acceleration, the rate of change of angular velocity, the rate of change of the rate of change of angle, is proportional to the sine of the angle. I can hear the wheels turning. Those of you in calculus are thinking double derivative of angle. And yes, this is a differential equation, but not an easy one to solve. The problem is the sine function. Here's a fun fact. It's called the small angle approximation. For small angles, measured in radians, the sine of the angle is approximately equal to the angle. Let's try a few values. Sine of 30 degrees, you should know this one, 0.5. 30 degrees is pi over 6 radians, approximately 0.5236 radians. What's the percent error in using 0.5236 for sine of 30 degrees? 4.7%. Okay, not great, but not terrible. Let's try smaller angles. How about 20 degrees? Sine 20 is about 0.3420. 20 degrees is about 0.3491 radians. Using 0.3491 for 0.3420, we end up with 2.1% high. Let's try 10 degrees. Whoa, only 0.5% off. Okay, so for small angles, we can use the angle theta instead of the sine of the angle. Let's rewrite our torque equation. The rate of change of angle is proportional to the angle. For those of you in calculus, what kind of function, differentiated twice, is the negative of the original function? If you said sine or cosine, you would be correct. The kind of motion that matches this equation is sinusoidal, sines and cosines of time. The deflection of the pendulum is a cosine function of t, time, or a sine function of t, or the sum of both sine and cosine. This is called simple harmonic motion, SHM. For small amplitude oscillations, we can model the motion of a pendulum as simple harmonic motion. According to theory, the period of the pendulum is proportional to the square root of length over gravitational constant. What happened in your lab? Did the period depend on L to the 0.5 power? And did the period depend on G to the negative 0.5 power? And that constant that you calculated, was it 2 pi? Hopefully the answer to all these questions is yes. Let's do a units check. That's 2 pi radians in one cycle. L, the length of the string, has units of meters. Little g, the gravitational constant, has units of meter per second squared. Radians are an invisible unit. Cancel the meters. Square root of a square, so the units are seconds. Phew! That's a good unit for period t. Next, let's see if this formula makes sense. What happens to the time it takes to swing through a complete cycle if the pendulum gets longer? Doesn't the time increase? Bigger L, bigger T. That's what the equation says. What if we go to a planet with a larger gravitational constant? Remember, gravity is what pulls the pendulum back to the center. If there's more gravity, shouldn't it come back sooner? G is downstairs in the formula. Increase G, and you end up with a smaller T. There's another quantity used to characterize simple harmonic motion: frequency. The units are hertz. Ouch! Sorry about that. Cycles per second. Hold on. Period is seconds per cycle. Can it really be this simple? Frequency's just 1 over the period? Awesome! I can remember that. Let's do a couple of examples before we call it a day. If you quadruple the length of the pendulum, what happens to its period? Well, undoubtedly, it gets longer. Call the period of the original pendulum T1 and the period of the longer pendulum T2. There's an extra 4 factor inside the square root. Remember, the square root of the product, x times y, is the square root of x times the square root of y. We can put them in separate apartments, so to speak. Square root of 4 is 2, so the new period, T2, is twice the original period, T1. How about a second example? What happens to the period of the pendulum if you travel to a planet with 4 times the gravity of Earth? Whoa, that's a lot of gravity. Again, call the original period T1 and the period on the new planet T2. There's an extra 1 over 4 inside the square root. Again, move the 1 over 4 into its own apartment and take the square root. The period on this new planet is half of what it was on Earth. That's all for now, folks. See you soon.